Thank you, Matthias, for the introduction. Thank you to the dean. Thanks to the organizer for bringing me here. It's most unfortunate, but I only arrived last night. So I missed most of the papers and presentations. Those I have heard today can only make me regret the 2 days I missed. It's also unfortunate that I arrived only last night, because that makes me very jet-lagged right now. So I thank the audience in anticipation for your patience and forbearance, because I'm going to read my paper, and I'm going to read a very boring paper, which is why I wrote it. And I may fall asleep while I read it. Sometimes that happens, and if that happens, just bring me a cup of coffee and I shall try to restart from where I stopped, or one page before, or one page after. That said, I have to change my glasses because I am an old man. Now I don't see the audience anymore, but I see my paper, and the audience can still see me, I hope. So, that's my slide number 1. That's right. And as Matthias, here known as Matthias, right? As already anticipated, my topic tonight, is the second digital turn. I call it the second because it's different from the first, which we, the design professions, invented in the 90s. We know what that looked like. It looked like this, and this. We know what it was about: the fold, the blob, the non-standard, digital mass customization, etc. We also know that the stuff we are doing today doesn't look that way anymore. It looks more like this, or this. When a few weeks ago I presented an earlier draft of this paper at a conference in London, there was a discussion at the end, and in that discussion it emerged that the rift between the first and the second digital style is also a generational divide. On one side, we have the old masters of the continuous line, blobmeisters, spline makers, streamliners. On the other side, a new generation of complexifiers, mess makers, discretizers. You see the smooth guy on the left. There is actually him in the pictures at the bottom, and the rough guys on the right. That's not actually them, something they do. With, of course, the older digital guys blaming the younger digital guys for all the usual juvenile crimes. Your stuff is not architecture, it ain't a building, it won't stand up, it isn't practical, etc., etc., etc. We know the story. We have heard it many times in the history of architectures. It's what old guys always say against the young guys. It always was like that. Why should that change now? And it isn't changing, of course, but in design terms, the difference between the first generation of digital spline makers and the second generation of computational discretizers is now so big that one may wonder, is there something else going on here? Something beyond the usual generational rant? Digitally intelligent architecture is by definition driven or inspired by the digital tools we use. So we should ask, have computers changed so much in 20 years? Are today's computers so different from those of 20 years ago? For at a glance, many would argue that computers are still pretty much the same. They still work the same way. And that's true, or almost true, because computers today are also way more powerful, faster, and cheaper than those of the 90s. And this may well be one of those little things that can make a big difference. 20 years ago, computation was still so expensive that we had to skimp on data all the time. We had to use data sparingly and cautiously. We had to invent so many tricks and ploys to compress data as much as we could. Today it's the opposite. Data is everywhere and it costs almost nothing. Today data is so cheap that you can splurge on it, pile it up, throw it away, waste it. Even it's a free data meal all the time. Some have called it the zero-cost information society. And evidently, this is not just a matter of technical performance. At some point, this becomes something else altogether, something more pervasive and potent, a cultural shift, a persuasion, an ideology, almost. Today, we call it the new science of data. A few years ago, many called it big data, but the expression has already fallen victim of its own success. Yes, evidently data is more and more easily available, and computation is getting cheaper and cheaper all the time. We have known that since at least 1965, when Moore's law was first formulated. But let's proceed now one step further and imagine that to the limit, at some point in the future, an almost infinite amount of data could be recorded, transmitted, and retrieved at almost no cost. Of course, a state of zero-cost recording and retrieving will always be technically impossible, but this is the trend, the tendency. And the trend, as we see it today, is going asymptotically that way. Now, if we admit that, we must also conclude that many traditional technologies of data compression will soon become unnecessary, as the cost of compressing the data, and sometimes losing some in the process, will be more than the cost of keeping all the data as found in its original state for a very long time or even forever. If we say data compression technologies, we immediately think of JPEG or MP3. But let's think outside of the box for a second. If we step back from our immediate technological present and have a look at the bigger picture, we cannot fail to notice that so many technologies we use, including many cultural technologies we have been using for centuries, almost forever, should be seen today as data compression technologies we invented over time to cope with a chronic shortage of data and of computational power. Today, this chronic shortage of data and of computational power all of a sudden has just ceased to be. As a result, many of these old cultural technologies are now technically obsolete. We don't need them anymore. Let me mention just a few examples. Think of one of the most ingenious inventions of Baroque mathematics: logarithms, which translate big numbers into small numbers and we have a way around. And crucially, translate the multiplication of two big numbers into the addition of two small numbers. Laplace, Napoleon I's favorite mathematician, famously said that logarithms, by reducing to a few days calculations that would have taken many months, doubled the life of the astronomer. And we could add today of many 20th century engineers who, using a logarithmic slide rule, like this one, could calculate almost everything in a matter of seconds. But would the use of logarithms and of logarithmic tables extend the life of a computer today? Not really. Normal desktop computers like this one today are so powerful that a few more digits in a number, a few more multiplications in a line of script, in most cases do not really make any difference, in the sense that computation wouldn't cost less or be faster if we used short logarithms instead of long numbers. Not surprisingly, today's engineers do not use logarithms any longer. Logarithms are a technology of data compression we don't need anymore. Or, to take another example closer to the daily life of the design professions, calculus is another extraordinary data compression technology. Like logarithms, a great invention of Baroque mathematics. How many points does this line or curve include or contain? As I studied in high school, plenty, an infinite number of them. Yet we can notate all of them with a single line of mathematical script. Two variables, x and y, and a few parameters, a, b, and c, which stand for numbers, are enough to count them all. With that line, you notate an infinite number of points. Isn't that miraculous? Yes, it is, and it was, which is why calculus, when they invented it, was such a good idea. But this is not the way a digital computer would do the same job, because a computer, I mean the machine, would write down a very long, dumb list of numbers that in pairs of x and y describe each one of those points, one by one, as many as needed. We humans wouldn't do that because we do not easily work with a list of 2 billion numbers. A line of script is much easier for us to manipulate. But this is what computers do. In fact, this is the only thing computers really do. This is the kind of stuff that humans don't like, but computers do well. In the 17th century, Descartes, Leibniz, and Newton found a way to use a very short script, just a few letters and numbers to notate conics. 50 years ago, Bézier and de Castelnau found a way to use similar functions to notate any curve whatsoever. NURBS are the culmination of modern mathematics. Not really that, but that gives the idea. Bézier finished the work that Leibniz and Newton had started. But this is not the way digital computation works. Digital computation, as the name indicates, starts and ends with discrete numbers. Calculus is a data compression technology that humans may still cherish, but today's computation doesn't need. And this is, of course, one reason why some of today's digital designers have already discarded the calculus-based spline that was so important for the new digital style of the 90s, and they have started to use computation to engage the messy discreteness of nature as it is, without the mediation of elegant, streamlined mathematical notations. The style resulting from this mode of composition is often called voxelation or voxelization or something like that. And just as an aside, but don't say that outside of this room. This remains just between you and me and the lamppost. But this also suggests that perhaps, just perhaps, our school curricula should stop obsessing on calculus, which was so important for modern mathematics, because calculus isn't important at all for today's computation and data analysis. If you think of it, all the mathematics we studied at school from the age of 5 to the age of 18 was aimed at making us calculus enabled at the age of 18. At the age of 18, we can vote. In Europe, you can drive a car and you know calculus. That made sense 20 years ago. But does it make sense today? Well, that was just an aside. And there are plenty of other instances to show that the mode of use of today's big data has already led us to abandon ways of thinking that were so deeply embedded in history that we would have thought them timeless and universal. Let me add one more example. Many in this room are old enough to remember when Google's Gmail was introduced. I cannot say that to my students when I teach because they're age 9, so they don't remember that. But on April 1st, 2004, this is when Gmail came out. And many thought that it was an April's Fool's prank, as Google always does them on April the 1st, but that one wasn't. And many may still remember Gmail's original motto, don't sort, search, which today is no longer shown. But it was for many years. Originally in 2004, when Gmail was launched, that meant that we should stop putting messages in folders the way we always did, but should instead leave them all incoming and outgoing in a huge random pile. No sorting, because when we look for a message, Gmail will search for it with a full text Boolean search on words and numbers and find it no matter where it is. Search, don't sort. We should stop sorting because Google is so good at searching. Now, since the beginning of time, or since the beginning of history, sorting or classification has been our tool of choice for information retrieval. We put things in certain places, following some order, so we know where to look for them when we need them. And more generally speaking, the idea that we must sort and classify events in order to make some sense of the world goes back to Aristotle. And it is at the basis of all Western philosophy and science. But now Google is training us to leave documents unsorted because digital search is now so fast that there is no need for us to manually pre-sort documents. This principle needs not be limited to media objects. When we understand the way it works, it may extend to physical objects of all kinds, which can be tagged and tracked using radio frequency identification. This may apply to random junk in a garage, to books in a library, or to the full inventory of Amazon.com, which, by the way, is indeed what is happening. Items of all sorts in Amazon warehouses, including books, are not sorted based on subject or category, as a library would do, but only based on a frequency of sale, following an order which would be perfectly meaningless to the human mind. No human could sort that, right? But what does it matter? Because no human will ever have to sort that, because robots will search in it. We don't need to sort, because computers, computation, and robotics will search. That's for them, not for us. Use the same technical logic, however, in our houses. We could keep potatoes and socks and books and fish in the same drawers or anywhere. We wouldn't need to remember where we put things or where things are, because whenever we need them, we could simply Google them in physical space, and perhaps even use Google glasses to do so, as this is one instance where Google glasses would have been useful. And I am certain that they will come back at some point as augmented reality or mixed reality or some other reality, which we will see at some point. In short, the Google search, don't sort logic is teaching us the basic of a new digital art, the most astounding, the most miraculous, the most supernatural of all digital arts. The art of finding stuff without knowing where it is. This used to be witchcraft, black magic. Not long ago, people were burnt at the stake for doing that. Today, it is part of our daily digital life. We do it all the time. And this same Google logic needs not be limited to space. It may also apply to time. If every event that ever happened can be recorded, searched, and retrieved, in many cases, the search for an exact precedent may replace many other technologies of prediction, including nothing less than modern science in its entirety. Indeed, in some fields of predictive science, from weather forecasting to material sciences, information retrieval has already replaced the traditional analytic cause-to-effect approach of modern science. Because many scientists have already come, reluctantly, I have to say, to the conclusion that sometimes, instead of calculating results based on mathematical functions and laws of causation, it is easier to assume that whatever happened before, if it has been recorded, if it can be retrieved, will simply happen again whenever the same conditions reoccur. This is, in a sense, the real spirit of today's big data. And it is not very different philosophically from what Galileo and Newton also thought. But Galileo and Newton didn't have big data. In fact, they often had very little data indeed. So they had to proceed in ways that were different from what we can do now. Let me show with an example the difference between the modern science of small data, that's Galileo, and the postmodern science of big data, which is us. Galileo, it was a long time ago, made plenty of experiments to study the breaking of beams under load. And he famously published some of his results in his last book, titled On the Two New Sciences of Mechanics and Local Motions. The original title was in Italian, but was in 1638. The book was printed in Italy, but Galileo could never see the book, because due to some little accident he had had with the Inquisition, everything he wrote could not be printed in Italy. So the book was printed in Holland. And Galileo never saw it in its lifetime, because the manuscript could go out of Italy, but the printed book couldn't go back to Italy. Well, that's a long story. Because this is, of course, revolutionary, or it was. But today, we need not repeat any of Galileo's experiments, nor any other experiment, to determine how most beams will break, because generalizing from those experiments and many more that followed, we have obtained some very general formulas that predict the structural behavior of most standard beams under most standard loads. These formulas that all engineering students learn in 2 weeks and then forgetting 2 hours, or remember for life, depending, can go both ways. These formulas describe in few clean lines of mathematical scripts all the beams that broke in the past and all that will break in the future in certain given conditions. This is how modern science works, or rather worked till now. Because let's put ourselves now in a big data frame of mind. And let's assume, again pushing the argument to the limit, that we can have access to a universally searchable digital archive of all structures ever built, where all life events, so to speak, occurring to any structure ever built are recorded in full, from design and construction to collapse or destruction. In that case, the best way to design a new beam would be to search for the record of a very similar one that was built in the past and to replicate that design if we are satisfied with its historical performance. It happened before, it will happen again. This way, a simple search would replace all predictive science, and we could design the safest possible beam based on the incontrovertible evidence of precedent without any engineering calculation, any science, any maths whatsoever. Just retrieval, no science. Just Google, don't calculate, search. If you cannot calculate it, look for a precedent. Does that sound like a practical joke? Well, it shouldn't, because this is what we have been doing for the last few years, thanks to the power of today's digital computation, only in a slightly different way, often without knowing, and more often knowing, but without saying. Let me show that with another real-life example that some of you may already be familiar with. Recent technical developments on the extrusion and the robotic winding and weaving of very thin filaments have prompted exciting and promising experiments, such as those recently pursued at the Bartlett by Alisa Androsek, Gilles, who is here, Daniel Wittrich, and others, and in Stuttgart by Achim Menges and his team. A couple of years ago, Achim Menges, Ian Knippers, and their research group published a technical article, explained how they had calculated a thin shell made with 2 kinds of fiber-reinforced polymers for a pavilion they built in 2012. For this pavilion, structural calculations had to take into account the complex geometry of the shell, as well as the density and direction of each bundle and layer of carbon fibers and of glass fibers wound together in it. The authors started with a geometrical and material layout inspired, as always, in their tradition, by biological models. We have seen more examples this morning. Then simulated the structural behavior of the first model using standard computational final element analysis. Based on the result of this first simulation, some aspects of the design were randomly tweaked, altering, changing the geometry of the shell or the internal layout of the fibers. The finite element analysis simulation was then rerun on this second model, and so on. The process was repeated many times over until the authors were pleased with the results. In this process of optimization by trial and error, every simulated model that was tested and discarded corresponds to a physical model that a traditional artisan would have made, tested, and likely broken in real life. Using digital simulations of structural performance, however, today we can make and break on the screen in a few hours more full-size trials than a traditional craftsman would have made and broken in an entire lifetime. Artisans of pre-industrial times were not engineers. Hence, they didn't use mathematics to predict the behavior of the structures they made. When they had talent, they learned by intuition, by trial and error, by making and breaking as many samples as possible. So do we today, using digital simulations. We may or may not intuit some pattern, regularity, or logic inherent or embedded in the structures we are tweaking, but that is irrelevant. By making and breaking in simulation a huge number of variations, at some point we shall find one that doesn't break. And guess what? That will be the good one. One may object, but even that may take too long. And of course, we have a solution for that too. Instead of doing many trials ourselves, one by one, we write a program that will do many trials in a sequence. And we look for the best results in that sequence based on some parameters we have chosen. We call this optimization or optimization, and we have software to do that, such as David Rutten's Galapagos, a grasshopper plugin. As David Rutten explains, evolutionary algorithms, in this case, work as little more than unimaginably massive trial and error routines, where at some point some random, absolutely random trials start to turn out areas or patches of better results. And when that happens, the software targets those values, drops the others, and starts a new run of trials limited to the values that appear more promising, and so on, ad infinitum, or in fact, so long as we are pleased with the results and we pull the plug. Now, no human would calculate anything that way, because it would take forever, and because, honestly, it seems a bit dumb. But computers can do so many trials so fast that using advanced computation, massive trial and error becomes a viable computational strategy. In fact, that's the best computational strategy, because that's the only thing computers really do. Again, these are things that humans don't like, but computers do well. There is one logic for us and one for them. Something we do well and something they do well. In the case of Hakim and of his historical team at the AA in London with Michael Hensel and Michael Weinstock in the early 2000s, this trial and error design process was famously inspired by Frei Otto's method of physical form finding. But this iterative routine is also very similar to the big data search and retrieve alternative to modern science I just mentioned. Whenever digital tools allow us to collect, record, and process huge troves of data, information retrieval, the search for a precedent, is more effective than the traditional application of analytic, predictive laws of causation. In the case of the 2012 pavilion, the structure was an experiment without precedent. Hence, no corpus of previous comparable instances was available for search and retrieval. In the absence of any such historical archive, what did the authors do? Well, they just made one up. They made it up themselves. Using the immense power of digital simulation, they created, virtually, just the historical archive they would have needed. They may not have seen it that way, but by simulation and iteration, they in fact generated a vast and partly random corpus of many very similar structures, but all failed under certain conditions. And they chose and ultimately built one that didn't. This is a far cry from how a modern engineer would have designed that structure. which is one reason why no modern engineer could have designed that structure. A modern engineer would have started with a set of formulas, establishing causal relationships between loads, forms, stresses in the structures. These formulas are typically used to calculate the resistance of a structure after it has been designed, but they often also drive and inspire our first intuitive design of it. This is because causal laws make sense somehow. By the causality they express, they interpret and provide some understanding of the physical phenomena they describe. Indeed, in the classical scheme of things, causality is seen as a law of nature. We like to think that the laws of mechanics, for example, spell out in mathematical terms the way beams, cantilevers, pillars, arches, or vaults function in reality. And the formulas of structural engineering have a meaning which we think is true to nature. Indeed, this meaningfulness and the structural theories underpinning it are visible in all the masterpieces of structural engineering, from the Eiffel Tower to Nervi's vaults. If we look at these modern structures, we understand, we can read and see the basic structural principles the designers had in mind when they first sketched them. But this does not apply to our current way of designing by form finding, or as I would say, to better demarcate this computational process from Frey's auto precedent, form searching. The power of big data applied to information retrieval and simulation makes the mathematical formulas at the core of modern structural engineering as obsolete as the yellow pages. Has any of you used the yellow pages at some point in the last 10 years? Or of the logarithmic tables still included in many engineers' pocketbooks, still in use when I was a student? This is, in fact, my own copy. Through computational form searching, we can already design new structures of unimaginable complexity. But precisely because it is unimaginable, this post-human complexity belies interpretation and transcends the small data logic of causality and determinism we have invented over time to simplify nature and convert it into reassuring, transparent, human-friendly models of causality. Why does this unimaginably complex structure stand up? And thousands, very similar ones we just ran through structural simulation don't. Who knows? Nobody knows it. Least of all its designers. And yet it does stand up. Using digital simulations, we know in advance it will, which is why we can build it. So this is what I think we should call at this point a new kind of science. Computers can already predict things, but modern science cannot calculate, and our mind cannot understand. In some cases, computers can already tell us what is going to happen, but they won't tell us why, because computers don't do that. Prediction without causation. Again, this is not black magic. It is just the way computers work, and the way we must let them work if we want to take advantage of their power. And this is what some digital designers are now trying to do. And this is one reason why the second digital turn, which is unfolding now, is so different and looks so different from the first one, which started 20 years ago. Thank you.
Thank you very much, Mario, for this fantastic lecture. Mario Carpo was so nice to agree to answer some questions from the audience. So if there's any questions, please. No questions. I can't believe
Good.
that. All right. So well then. There's something.
Thank you for the great lecture, Mario. I think that we could argue that the organization of our cities through blocks and through streets and neighborhoods is a type of sort mentality by which we organize and understand and navigate ourselves. However, the advent of Google Maps and the fact that we all carry around Google Maps in our pocket, at least for me, has meant that I can never find anything without my phone. I am wondering if you think that the advent of augmented reality and the element of that even more personally, not just on a phone or even as a phone, will change the way that we think about building and space planning in the way that Google Maps has changed the way that we move through the city.
That's a very good point, because can you still hear me? Because I made an example at the micro scale and an example of architectural or interior domestic scale with the example of the socks and stuff at home, which we classify, well, because it is a frame of mind. Some people like order, some people don't, but no matter what, it's a practical need. We put things in certain places so we know where we are when we need to retrieve them, which is why all the winter socks are in a drawer, all the summer socks are in another drawer. That doesn't happen in England because it doesn't have seasons, but never mind. So there is a practical need to do that. The moment a technology allows us not to sort because we can search, at some point we shall stop doing that. When Gmail came, many people thought, I will keep using folders because I always did it. And this is what I thought 12 years ago. But now, much to my detriment, and we could make a test to see how many followed, but I don't use folders anymore. I still use some folders for some specific project, but most of the time I have to come to the conclusion that indeed Google can search better than I can sort. Because to achieve the same results, I should have had the same taxonomy in my mind, always the same, for 12 years, which doesn't really happen. So, at the urban scale, it is true, since there are increasingly artificial intelligence tools that allows us not to remember locations and not to classify locations because they can search better than we can sort, probably the same phenomenon is happening. Will this apply to the modernist idea that cities as a repertoire in the catalog of function should be sorted? This is a more complicated philosophical issue. Generally speaking, if cities become messier, I think it's good. Cities always were messy until modernism came and decided to classify cities. Le Corbusier called it la ville classée, the city sorted. But if we can move out of that, I will not complain if Google Maps is one of the tools that can make that happen. This is just my personal opinion.
Mario,
you run, you choose.
Thank you for an extraordinarily beautiful and compelling talk. At least a sense of beauty that I feel when I think about standing and feeling and navigating as an individual in peacetime, in times when I can search and reflect and look at the actual circumstance of finding real things, rather than being dependent on the assertion of something which is much more global or something which is much more abstract. And yet, I must say I have a kind of a horror in response to what you've said as well, in the sense that alongside the beautiful sense of involvement, of being able to look at true, real things that have happened and to base my decisions for change on them, the hurricane is coming, and the storms are around, and things are dying, and there are questions that I feel, at least I'm trained to feel, need nationhood, need citizenship, need the ability to propose profound, transformative change. What are the implications for your provocation for the idea of the common and for nationhood?
This is beautifully said. The simple, immediate conclusion of the premises of my talk is that in order to make some sense out of this, we should reverse the Turing test. Turing's idea that computers are good when they do the same as we do. This is wrong. Computers are good when they do something completely different. There are two different logics. Google said it, search or sort. We should keep all the sorting for us, because that's the only thing we can really do well. We are not good at searching. It takes too long. But sorting, that's something which is specific to us, and that computers cannot, and in my opinion, time will prove me wrong, they will never do very well. So instead of arguing for the equivalence, the idea of the Turing test, let's make a clear demarcation. There are two logics, one artificial, one natural. Let's keep the natural for us, and let's leave the artificial for them. Let's not force them to imitate us, because they cannot do that very well. But let's not try to imitate them, because we are not good at that. I think this is an important point, which we should bear in mind. And if we can keep this demarcation clear, it will be better for all, even for the machines, if they could think.
I don't know. You started off the lecture talking about the second digital turn in terms of a new style. You refer to style quite often. I have an analogy to that. We had another speaker who was speaking, Theo, not about form and those kind of questions of style, but was talking about information. And it seems to me, if we're going to think about what's happening now, it's precisely, and especially the way that data's being used, it's precisely in terms of this kind of logic of information. I mean, I got an Uber to get here, and it's that kind of smart use of technology that really the world is all about now. It's not about making sexy parametrical, whatever it is, parapatric buildings, we should say. And in terms of Google, actually, I don't know if you're aware, but Flint Diller produced what's called a game called Ingress. Ingress is actually not a game. It's Google trying to gather data about the city. I mean, they're interested in kind of property and so on, and those kind of things. And it seems to me that is the kind of the way that we're going. And especially here in the States, where, I mean, you must have read the news about hacking your emails and so on. It's kind of like the things that Ben Bratton has been talking about for a long time in terms of the stack, in terms of the kind of the way that's where kind of warfare is being played out in many kind of ways today. So if there is a second digital turn, I think maybe we don't even use the word digital anymore. It is kind of surely towards the kind of use of information and what it's all about. And it's not about style. That seems to me something terribly postmodern. And maybe historians talk about things this way, but I don't think it's so productive.
I know that use of the term style is always disturbing for many, and perhaps at some point I should just drop it, because I don't really mean style in the philosophical, art historical sense of the term. I just want to refer to the simple, inevitable fact, but in the design professions, what we do at some point will have a physical form. And at the end of the day, what we do, we can have the best ideas in the world, but if they don't look in some kind of way. People will not pay us, they will not hire us, they will not publish our work. At the end of the day, in the design professions, we cannot avoid, we cannot duck, we cannot escamotage the problem of making form. And so we have to keep bearing in mind that the visuality of what we do is important, because if it doesn't look good, no one will pay us. I'm sorry, I wish it weren't that way, but it is that way, and we cannot avoid to bear that in mind. But I agree, I should probably find at some point, to avoid disturbing every time 15% of the audience, the use of the term style. And I should replace it with code. I should call it X2759.6. And then we shall all be happy. But we shall still be making form. And when we make it, we shall always ask, what does it look like? And does it look like something else that someone else did 2 weeks ago? This is the kind of stuff we care about, because we make physical stuff. We are a design profession, it's our job. If we don't like it, we should do something else.
But I mean, so just maybe pick up on that, because sure,
No, over.
Things look like
It's over.
There's an effect. But I think that the shift that we've had in the logic of the search has been away from representational discourse towards process-based things. And actually, when you think in terms of style, you're looking towards something, whereas you search possibilities out and the computer helps you sort out the range of things. So I do think one has to kind of change the frame of reference completely. And I do think style is super problematic in today's context.
Agree.
Thanks so much for the
I thought that was the last
inspiring lecture. My question is tied to, I think it's a fantastic lecture. Some recent studies have been made that have identified some problems with search, not in its effectiveness, well, but yes, maybe inherently in its effectiveness, in the sense that many of the search engines that we rely on have been demonstrated to inherit our cultural biases, so gender bias and racial bias. And we in this room are generally a group of tool makers who are either making tools for ourselves or tools for other users who may have better search options through the tools that we make. What kind of ethical mechanism or what kind of strategy can we employ to ensure that we're resisting the implicit biases that our tools are given?
That's a very good point. I've been talking about search in abstract, philosophical, purely ideal terms. My idea of search is that you're looking for the word Adam in a textual database. It means that the computer will scan a sequence of 0 and 1. And when it finds 4 letters, it is 4 octets or bytes. So when it finds the same sequence of 32, 0 and 1, the computer stops and the bell rings blank and it flashes. This is the way a search using a word processing in 50 pages actually works. But every time that we punch a sequence, an alphanumerical sequence in Google, Google doesn't scan the World Wide Web looking for a sequence of 0 and 1. In fact, the World Wide Web has already been copied, and I shouldn't say that because it goes counter to my argument, but indexed. So Google can search so effectively because that archive has been classified using traditional library sciences. But we would like to think that that is a shortcut, and that the ideal digital search is just a search on a bland sequence of 0 and 1. Mathematically, that's the way it should be. In practice, Google is so good because the shortcut they came up with 25 years ago was genius. And by the way, no one knows really how it works. But we know it is based on a system of classification, and it comes from library sciences. So it is basically sorting, not searching. But when you use it just as an interface, it's search, not sort. So if you look under the hood for the nuts and bolts. It doesn't work that way. It doesn't work the way I said. I just took it as an extreme example of how it could work if the world was made of 0 and 1, which is not yet the case.
So I know that there are still more questions and we can go on with this fantastic conversation, but I would like to thank, first of all, Mario Carpo for this fantastic lecture and answering of his questions. Thank you very much.
Thank you.